This is central Wales. On over 200 days every year, it rains. But the rain causes a lot of damage. After every storm, you can see where the stones and soil have been swept into the streams. The land has been eaten away. This is called erosion. Once in the stream, the stones can be swept away if the water is flowing fast enough. If you look carefully at a stream, you'll see the water moving at different speeds in different places, and this affects the way the stones are moved. To find out more about these effects, Science All Around went to see Malcolm Newson, a scientist who studies erosion. In fairly slow-moving water, the small stones are swept away. Now let's see what happens in a faster part of the stream. It's only when the water is flowing really fast that bigger stones are moved along. Part of Malcolm's job is to find out how much land is being lost, to find out how much erosion is taking place. He needs to examine the stones, and to do this, he's built a trap. Any stone carried along by the stream falls into the trap. The trap is emptied once a month, but Malcolm doesn't have to examine all the stones. The stones are piled up around these boards, and the boards are important because they allow Malcolm to take a sample, to take only a part of the load. Here's how it's done. The digger drops each scoopful on top of the central pole, but only a part of each scoopful falls between the boards. Now let's look at a diagram to find out how the boards help Malcolm to take this sample, to take only part of the load. If we look at the boards from above, you can see that they mark out 1/8 of a circle, and so they cut out exactly 1/8 of all the stones that are dropped on the central pole. And that's the sample. That's the part of the load that Malcolm uses. Before the sample is taken back to the laboratory for examination, it's weighed. Malcolm can work out the weight of all the stones when he knows the weight of the sample. This sample weighs 60 kilograms, but that's only 1/8 of all the stones. So by multiplying 60 by 8, Malcolm knows that all the stones that were caught in his trap weighed 480 kilograms. Now, 480 kilograms happens to be the weight of the stones that Malcolm found in his trap in January last year. Each month, he's kept a record, and we can look at the sort of chart he used last year. First of all, in January, we know that the figure was 480 kilograms. In February, there were 410 kilograms of stones in the trap. And in March, Malcolm found that the pile of stones weighed 370 kilograms. And so he went on recording the amounts month by month throughout the year. Now let's look at the sort of chart that Malcolm used to record how much rain fell each month last year. In this part of Wales, January is the wettest month. February is not quite so wet. Less rain fell in March, and the pattern for the whole year looked like this. Let's compare this rainfall chart with the chart for the weight of the stones. You can see that there's more erosion in the winter than in the summer, when the rainfall is less. In the lab, Malcolm's first job is to sort out the different sizes of stones in the sample, using a sieve. Stones larger than the holes can't get through. Stones that do fall through have to be sieved again, through a sieve with smaller holes. But sieving by hand would take far too long, so Malcolm uses a machine. After picking out the very large stones, the rest of the sample is put in the top sieve. To make sure none of the sample is lost, the lid is fixed firmly in place. There are 8 sieves which are shaken automatically. The sieve with the largest holes is at the top. The sieve with the smallest holes is at the bottom. The stones are shaken down until they reach a sieve with holes they can't get through. Using the machine, it takes only half an hour to sort out the different sizes. When the sieves are emptied, you can see for yourselves that all the stones from each sieve are about the same size. And also, interestingly enough, they're all roughly the same shape. They're neither sharp-edged nor are they round. Now this isn't surprising because the shape depends on where you find the stones, on how far they've been moved by the stream. Up in the mountains, the stones which have only just fallen into the stream are all shaped like this: rough surfaces and sharp edges. But as stones are moved along with the stream, they rub and knock against each other, becoming smoother and rounder. The further downstream they're carried, the more knocks and bumps they get, and the rounder and smoother they become. The stones also bang and rub against the rock over which the stream flows. When the water's low, you can see how this rock has been made smooth, and where, in parts, it's been hollowed out. Then there are potholes. A small whirlpool has swirled the stones round and round. As well as cutting a hole in the rock, the stones have become very smooth and rounded. So in this part of the stream, it's the bumping and grinding of the stones on the rocks that causes erosion. Lower down, the landscape changes. The stream becomes a river, curving and carving its way through the countryside. Here, the land suffers from a different kind of erosion. The banks are made up of soft, crumbly material, which is easily washed away by the fast-flowing water as it cuts its way into the bottom of the bank. Because the material is made up of very small particles, it's easily carried along in the water. To find out how much is being carried away, Malcolm needs to take regular samples. Here's how he does it. The bottle is fitted with two tubes, one of which faces forwards into the flowing water. The other faces backwards to let the air out of the bottle as the water goes in. Malcolm raises and lowers the bottle so the sample contains water from all levels. Soon, Malcolm has a sample of water containing some of the fine, solid material that's being carried along by the river. To find out how much solid material there is, he has to separate it from the water. This is a special kind of paper called filter paper. A filter paper is a very fine sieve. The holes are so small that only water can get through. It's held in a special funnel, and Malcolm pours the sample in on top. In the funnel, the fine solid material makes the water look cloudy and dirty. But as only the water can pass through the filter paper sieve, in the flask below, the water is clear and clean. The solid material trapped on the filter paper is now dried in an oven. Here are 5 filter papers which show how much solid material Malcolm collected at different times during the year. The first was collected when the river was in flood. The others when there was less water flowing, and so less cutting away of the solid material from the banks. By the time a river reaches the sea, it's carrying thousands of tons of solid material. These mud banks are built up from that material, which has been eroded from the land farther upstream. But not all of this land is lost. Here in the Wash, a seawall has been built, and soon potatoes will be harvested from the land that has been reclaimed. This is North Yorkshire. Here, most of the rock is limestone. Now, one of the characteristics of limestone is that it dissolves in rainwater, and some unusual things happen in this area. Streams disappear into holes in the ground. These men are experienced cavers. It's through their explorations that we know what happens underground. This maze of underground caves and passages wasn't cut out by the movement of stones. Just like sugar dissolves in your tea, the limestone has been dissolved in the water. In the older caves, there are stalactites growing from the roof. They are columns of limestone, some of which have been growing for thousands of years. As water drips from the roof, some of the dissolved limestone reappears, slowly adding more material to the growing stalactites. In the same way, the dissolved limestone reappears from water dripping onto the floor and forms stalagmites. But you don't have to wait for thousands of years to see dissolved limestone reappearing. This is Mother Shipton's well at Knaresborough in Yorkshire. Here, the water contains large amounts of dissolved limestone. Any objects hanging in the dripping water quickly get a hard coating as the dissolved limestone reappears. There's so much limestone dissolved in the water that objects become coated in under a year. Now, the limestone that covers the objects at the well was first dissolved by rainwater, so material that dissolves in water can reappear. The sea covers 4/5 of the world. If you've ever been swimming and had a mouthful, you'll know it contains salt. Millions of tons of salt are dissolved in seawater. In North Australia, the sea is a major source of salt. The sun beats down on huge, shallow lakes of trapped seawater. Slowly, the water evaporates, driven off by the heat from the sun, and the salt reappears. When the salt is dry, the machines move in, and thousands of tons are collected. If you examine salt under a microscope, you'll see lots of tiny crystals, each with the same characteristic shape. To find out how to make crystals, we went to Oxford University to see Peter Walker, an expert on crystal growing, who showed us what to do. First of all, Peter pours out a measured amount of water. Then a measured amount of a substance called alum is added to the water. Eventually, after stirring, the alum disappears, giving a clear liquid. Whenever a substance dissolves in water, the resulting liquid is called a solution. Peter puts the solution onto a hot plate to drive off the water. As the water boils away, the alum begins to reappear. Boiling is a fast form of evaporation, and soon the water is driven off and all the dissolved alum reappears. Now that beaker really is very hot, but Peter is used to handling very hot apparatus. Apart from being a bit damp, the alum hasn't changed. Boiling, fast evaporation, hasn't produced any crystals. It's much the same as it was when we started. In order to get crystals, the water has to evaporate slowly, and so Peter takes another sample of alum solution and pours it into an open basin called an evaporating basin. The evaporating basin is put on one side, and after 2 or 3 days, the first small crystals appear. Over the next few days, the crystals grow, but by only a small amount. If you want to get really large crystals, you have to make a special solution. And to do this, Peter heats up a solution which is already full of dissolved alum. Now, hot water can dissolve more alum than cold, so while it's hot, he adds more alum. When this solution with the extra alum in it cools down, it becomes the special solution that you need to grow really big crystals. You have to be careful and keep the special solution covered to stop dust getting in. The best way to make a large crystal is to start from a small crystal called a seed crystal. You should look for a suitable seed crystal among those you made by slow evaporation. Now remember that the best seed crystals are not necessarily the biggest, but the ones with the best shape. Once you've chosen your crystal, it has to be glued to a piece of strong cotton. You need just enough cotton so that when the other end is attached to the dust cover, the crystal dangles about halfway into the special solution. Now, you just have to wait.